Okay, so I'm very happy to share my work on private aggregation. So Ryan just talked about how to do it in the two-server setting. And in this talk, we're going to look at the single-server setting. Okay, let's see if the clicker works. Okay, great. So our target application considered here is something called federated learning. So FL is a mechanism that allows a centralized server to train the models on user data without explicitly collecting their data. So to understand the setting a bit more, FL runs in many iterations among the server and the clients. And in each iteration, a set of clients is going to receive a model from the server, and the client are going to update the model by running a training algorithm locally on its own data. And that will result in a so-called local model, which I show here as a floating point vector. Then the server is going to collect these local models from the clients and average them to get the global model. However, a line of work has shown that this local model actually leaks information of the user data that it gets trained on. So as a result, researchers in the past have proposed to apply private aggregation in this setting. So private aggregation, just to recap a little bit, allows the server to only learn like the sum of the inputs from the client and what's implied by the sum, but nothing else. So in particular, the server doesn't learn which like individual input of the client. So here the xi is going to be the floating point vector, and then such private aggregation will run many times for each iteration in the federated learning. Okay. So although there are many private aggregation protocols out there, very few truly fit in the federated learning setting. The reason is that FL comes with a set of very specific system constraints that most of these protocols were not designed to account for. So the first challenge is that FL in practice assumes a single untrusted server. So if you look at large companies like Google, Amazon, JP Morgan, they all favor this single server deployment architecture where a central server coordinates the training of all the clients. So really, the aggregation protocol needs to guarantee privacy against this untrusted server who coordinates everybody. And at the same time, there is also constraints at the client side. So these clients are mobile devices with limited compute and unreliable participation because they are like phones, laptops, very lightweight devices. And this implies that our private aggregation protocol really needs to be designed in a way that it's efficient enough to run on our devices like phones or laptops. And also these protocols need to handle failures, which means that the protocol should still output a valid result to the server, even if arbitrary clients just drop out during the execution of the protocol. Okay. And because of these constraints, these classical multi-server solutions, including those that were discussed before, while they're very, very efficient, do not work here just because of this model. But we can still borrow some ideas from there. So specifically, these multi-server solutions usually start with having the client secret share the input data X, and each server sees only one shares and hence learn no information of X. So now if we have a single server, we cannot sort of distribute trust among the servers in that way. But the classical idea is that we can distribute the trust across the clients instead of the servers. So a naive solution is we just run a giant generic MPC among all the clients we're going to run aggregation on. And but this runs into a problem that multi-party computation usually requires these clients have point-to-point communication channels, and also it requires each client to talk to every other client. In federated learning, first, we do not have this point-to-point channel because these clients are phones and they don't know each other's identities. And also because like each iteration will have hundreds, thousands of clients. So really requiring each client to talk to every other client is just infeasible in practice. And also, this naive approach is unclear how it is going to handle the failure. Okay, but using this idea of distributing trust among clients, prior work has designed customized protocols that greatly improved communication computation costs at client over the naive one. For example, the first work is done by a team at Google, where they improved the client communication from the input length times number of clients to only the additive factor. And then later, there's a very nice work that achieves only polylogarithmic overhead over the plain text setting. These works largely follow this pattern where the server communicates with all the clients for 6 rounds to compute one aggregation instance. These are like very nice asymptotics, and they make clients work no longer a bottleneck. But now, if you look at the end-to-end performance, it's actually bottlenecked by rounds. So not only it's the number of rounds they need to run for one aggregation, but also each round, the server needs to interact with all the clients. And the issue with the second point is that their design really requires the server to wait for a sufficiently number of clients to respond before they proceed to the next step of computation. In a bit more detail, so if you look at like one round in the protocol, it works like this. So the server will first announce to the clients that, okay, like this round trip starts. Then after the clients receive the messages from the server, they started some local computation. Some clients are faster, some clients are slower. And then the server set a timeout period just to wait for the clients to respond. And some of the clients are going to drop out here, and the server will not continue to wait on them, and then collect these messages and process this in this round. And then after the server finishes the processing, the server will announce to the clients again and repeat this procedure for the number of rounds in the protocol. And because prior work, they really have reduced the client computation and the server computation to really a small part, like a small part of the whole process. So the performance is going to be bottlenecked by this waiting time. And a natural question to ask here is that, can we just decrease timeout? A direct consequence is that there will be fewer clients included some, but the more severe one is that this will break the failure tolerance guarantee that this protocol has. Yeah.
So these models are pretty big, right? I imagine. So is it not the bandwidth that's kind of the bottleneck?
So we run some simulation. It's actually not the case.
I see. Yeah, interesting. Yeah. So how many megabytes like per round for?
So just to clarify, like these models are running on the client, client devices are not like large language models. So they're like vision models, like Cypher 100. I mean, like a little bit bigger than that. So training on like these kind of like data sets. So yeah, it's like a few. I don't remember the exact number, but it's not like gigabytes or something like that.
I see. It's like megabytes per round or something.
Yeah.
Okay, cool. Yeah. Thanks.
And also like just to mention, because these clients are like geographically distributed, and like our simulation is sort of like simulate like, it's not like, oh, we set up the clients in the same like region and then they all have like similar, network condition. So like we set up the simulation in the way that it's like, like there's a long tail of the network latency, so that there's like really some stragglers that makes this waiting time really long. Yeah, I mean, we can discuss this offline. Yeah. Okay, so if we cannot naively reduce the wait time, how are we gonna like improve this end-to-end performance? Our observation is here is that if you look at like private aggregation, like just in theory, essentially only one round really needs the server to wait on all the clients, and that's gonna be the round that the server asks all the clients to submit their inputs, but in some mask form. And after that, unmasking or revealing the result to the server doesn't fundamentally need all client involvement. This inspires our approach, which is a new sort of aggregation paradigm. Instead of these homogeneous rounds, we're going to divide the aggregation into two phases. In the first phase, the server just asks the clients to send the mask inputs. And here the server talks to all the clients. And in the next phase, the server will interact with a small subset of the clients who will help to unmask the result. And these small set of clients are randomly selected from the total population during some setup. And the server here just need to wait for a fraction of them to respond. OK, so if we ask this question again, like, can we decrease the timeout? On the first round, the answer is no, because we still need to wait for the clients to submit their inputs. But on the rest of the rounds, where the server only talks to committee, we can just decrease the timeout and get the sufficient number of messages as long as we can recover the result. OK, so these are the design paradigm for the two works that I'm going to talk next. The first work is Flamingo. And in this work, we have a two-round aggregation protocol in the semi-honest setting and the three-round protocol in the malicious setting. So here, by like 1+1 and 1+2, I mean that the first round, the server talks to all the client, and the malicious version only incurs like one more round where the server talks to the committee compared to the semi-honest version. OK. So to get into how this protocol works, the first step is, go ahead.
The malicious setting is where the committee is malicious, or the server is malicious, or some of the clients?
Oh, OK. So the threat model here is that the adversary will control the server and a subset of clients in the beginning of the protocol. So you don't know, like, some of the committee clients may also be malicious.
OK, thank you.
And then when you start the protocol, they run some setup where a small set of clients are randomly sampled as the committee clients. So yeah, so in the aggregation, like some of the clients who submit their input could be malicious, and some of the committee clients can also be malicious. And the server is malicious as well, yeah. OK. So the first step is to set up some pairwise secrets between the clients. Just to give example, let's say we have 3 clients. So the pairwise secrets really means that S12 here, shared by Alice and Bob, is not known to Charlie. OK, once they have this pairwise secrets set up, each client can just use this to mask their input and send to the server. And the masking is done in a special way such that when the server adds up the messages from all the clients, these pairwise secrets are going to cancel each other out, and the server will get exactly x1 plus x2 plus x3. OK, here I just show 3 clients, but this approach can be generalized to any number of clients. So let's say you have n clients. You can set up a complete graph between these clients and set up secrets on the edges. And there is later optimization showing that you can sort of set up a sparse connected graph over the clients, and then only set up the pairwise secrets on the edges in the sparse graph. And that will improve the computation and communication cost. OK, but in this work, recall that these inputs are like model weights in federated learning. So really, we need to use a pseudorandom generator to expand these pairwise secrets in order to mask the long vector. OK. This pairwise masking approach is really, really efficient, but it does not handle failures. So for example, if Charlie dropped out when the server asks the clients to send the masked inputs, what the server gets is y1 and y2. But adding them together will not get the server x1 plus x2 as we desired. So the reason is that the masks associated with Charlie are not canceling each other out. And a direct sort of solution is maybe we'll just reveal the secrets to the server, and the server can just subtract them from each vector. And this is actually still private because each input of these online clients is still masked by their pairwise mask between them. OK, so now it seems that we have the solution, but the question is that how are we going to reveal these secrets to the server? And the tool we'll use here is something called threshold decryption. So in threshold decryption, there is okay, the server runs with a set of community clients, and the result of the protocol is that the server will get a public key, and each of the community client is going to get a piece of the secret key, and no one knows the full secret key. And if the server encrypts or like gets some ciphertext that's encrypted by the public key, then it sends to the community client. Each community client can decrypt this ciphertext and get a piece of decrypted result. And then the server can gather all these decrypted results and recover the underlying plain text. So now we're going to modify the step 2 that we just showed before. In addition to having the client mask their input, we also ask the client to send some public key encryption of the pairwise secrets that are associated with them. So for example, here I just show what the messages that Alice sent. So it also sends encryption of S12 and S13. Now, if Charlie drops out, the server can just parse this encryption of S13 and ask the community clients to decrypt. Yeah, so this is the way that the server will get, we're going to reveal the secrets to the server. OK, so this is the entire workflow of Flamingo. So assume we have these setups. Then the server will announce to the client that this iteration starts. Then each client is going to locally compute this mask input, sends to the server along with the public key encryption of the secrets. Then the server is going to process it by adding this up, adding the mask vectors up. And then the server will identify which client drops out. And it will ask the community clients to decrypt the secrets on the edge between the online clients and the offline client. And then the decryptor sends back the result. The server will parse it and subtract them from the sum that it gets before. OK. And finally, in this workflow, I want to say that we really require a one-time setup. So as I showed before, these pairwise secrets are essentially one-time paths, so you cannot reuse them if there's the same client selected in federated learning. So what we did here is we're going to use these secrets in the initial setup as a long-term secret. And then we'll derive a short-term secret, or like iteration-specific secret, from this long-term secret S12. And this iteration T is a public number. You just have this counter and then have S12 as the private key, as a key in PRF. And then everything in the workflow is just gonna do it with the iteration-specific key, specific secret, but not the long-term secret. OK, so yeah, just to get back to Henry's question, we like run some simulation, and the simulator we use is some tools that developed at JP Morgan, where they use it to simulate client transactions. We implement our protocol based on that, and sort of extract the actual wait time of the server in both our protocol Flamingo and the best of prior work developed by Google. And really, you can see that just like by looking at the wait time, you can like save up to like a factor of 8. And this is mostly because in the round 2 and round 3, we only need to wait a fraction of the committed clients. OK. Any question here? Yeah.
What happens if some of the committee members drop out when the server sends them the encrypted secrets?
Yeah, so like we have a threshold set for the committee. So if like the committee clients who drop out throughout one iteration is larger than that threshold, then our protocol can proceed. And this threshold is 2/3 for the second round and 1/3 for the third round. Yeah. Yeah.
A few years ago, some folks at Brave proposed a scheme called STAR for using threshold aggregation for private, threshold encryption for private aggregation. The attack that they couldn't solve, though, was one where a sufficiently large coalition of malicious clients stuffed the aggregation with like synthetic reports where they know the value, but then enough of them to meet the threshold that the server wants so it can decrypt. And then what they can do is like subtract the known value of all their fake contributions and recover a target value. So does your threshold aggregation scheme have defenses against coalitions of malicious clients?
Okay, so no. So for example, if like a majority of clients in the population is malicious, then you could break this guarantee because we randomly select clients from, like community clients from the total population. Yeah, I guess it's also, just one sentence. Like, I guess it's also like, I don't know whether this is fundamental, but it's a limitation for most of the single server aggregation protocol I know, because really the theory behind is that we distribute the trust among the clients, and the privacy really relies on, majority of them being honest, yeah.
So maybe one clarification question. So I guess in the protocol that you showed, it seems like the server could, in the case that the server receives all the reports, it could still claim that it didn't receive my report.
Yes.
And then the system will basically tell, my data will be revealed to the server. Is there some way to prevent that?
Yeah. So the thing I show here is the semi-honest version, where the server just follows the protocol. In the malicious version, we have another round in between this. And that's something where the community clients cross-check if they have consistent view from the server. And also cross-check if the server reported is like above some threshold. So in that way, we guarantee that even if the server can, arbitrarily drop some clients' messages or send inconsistencies to community members, there's sort of a bottom line privacy that we can guarantee there. Yeah. Okay. So the next work I'll present is Armadillo, and the architecture here is like very, very similar to Flamingo, but here we achieve something that's called a robustness, which Ryan covered a little bit before. Okay, so just to recap, like why this problem is actually challenging here is because if like malicious client sends some invalid input to the server, because this is private aggregation, the server doesn't see like the messages, so the server needs to check whether this message is valid without like learning the information of it. And the robustness guarantee we're gonna have here is even when some clients misbehave in the protocol, the server can always learn the sum of the inputs of those valid ones. And this actually implies two things. The first one is that the server should be able to reject malicious input. This is similar as what Ryan talked before. The second one is that if the client deviates from the protocol, and that should not affect the execution, and the server should be able to output some eventual outcome. Yeah. Oh, okay. Yeah. And in this work, we're interested in considering like checking the norms of the vector, which are L2 norm and L infinity norm. And the difference for the threat model from Flamingo is that we only consider server here to be malicious, but the clients here can be, server to be semi-honest, but the clients here can be malicious. Okay, so I will only give you like a general like recipe and workflow of this protocol. I'll not go into like details of that. So like to have the client, to force the client to correctly follow the protocol, a generic way to do this is we can just have the client to prove that they have been doing the computation correctly. And because our protocol only have the first round where all the clients sort of computes and the master vector, we can just have the clients to prove that they do the first round computation correct. And the computation is just a sequence of additions and multiplications on private and public inputs. And the generic way is to just throw a zero knowledge proof for this sequence. But the problem is that zero knowledge proof is expensive. So really, we want the sequence to be simple, meaning that we really want the client local computation to be friendly to zero-knowledge proof. And because of that, we redesigned the aggregation so that the client side only has very simple arithmetic computation. And this design allows each client to write the proof statement as a single inner product relation. And for the first one, we will use a tool called key and message homomorphic encryption. So this means that if you add up two ciphertexts under this encryption, you're going to get one ciphertext that encrypts the sum of the messages under the sum of the keys. Okay, so in this protocol, these X are going to be the floating point vector, the plain text we're going to aggregate on. And each client, they will freshly generate the key for this homomorphic encryption. Then the server gets all the vector Ys, and it sums them up and gets a single ciphertext that encodes the sum of the inputs. But now the problem is that how the server is going to decrypt this result, because the server needs to know the sum of all the SIs. To do that, in the first round, we let the client also additionally send secret shares of the SIs, but in some end-to-end encrypted form. And then in the next round, the secret shares of these SIs are going to be forwarded to the committee member who aggregates them locally. And then the committee members will respond to the server the secret shares of the sum of the keys. And finally, the server is going to decrypt the ciphertext by reconstructing the shares and applying on the ciphertext. OK, so this is sort of the design of the redesign of the aggregation. And for writing the proof statement, we're going to use something called inner product proof. So this means that if you have two private vectors, A and B, you can prove an inner product statement on these private vectors sort of like efficiently with very small proof size. And, oops. OK, so I'm not going to go into detail of how we write this proof statement as inner product relation. The key point is that here the clients only need to prove two things. So the Ys is correctly computed from the homomorphic encryption, and the input has legitimate norms. We can write, we can just bundle them together and write this as a single inner product relation and have the clients send the proof to the server. Then the server can batch check all the proofs from clients with the complexity only logarithmic to the number of clients. OK, so how much time do I have? OK, I think I'm getting to the last slide.
Maybe we should just skip to the, I want to make sure people have time to get lunch.
Yeah. OK, so the progress, there's lots of progress made so far, starting from optimizing over naive MPC, and then this new architecture and so on. And there's many more under the committee model, which some of them are going to be covered by people who give talk in the afternoon. And finally, I want to mention there's a very interesting result come up very recently that they improved the committee cost to only O of 1 by combining Flamingo and the new result in batch threshold decryption. OK, so this is my last slide. So there are many interesting open questions to explore here. So the first one is, how small can the community cost be? I just showed that they reduce the cost to O of 1, but that's asymptotic. And how concretely can we make this small? And the second question is that, what if the adversary is adaptive? For example, in this iteration, the adversary corrupts this set of clients. In the next iteration, the adversary moves and then targets on some other clients. And the third direction is that in this work, we only consider checking the norms of the vector. But there are many works just in the learning community that saying, oh, this is not enough in all kinds of different ways. So how can we incorporate this additional like defense mechanism into private aggregation. And finally, we can also consider this problem under this community architecture for a richer functionality of class. And initial work is started by these group of people recently into 2024. And that concludes my talk. And thanks for staying before the lunch.
Maybe take one question and then head to lunch.
Great talk, thanks. I have a question on the zero-knowledge proof in the end again. You compare Acorn, I think, with Armadillo, and I was wondering, like, what is the technical difference there in terms of how you implement the norm checking? Because as I remember, I wasn't on the Acorn paper, but I remember they also use some reduction to inner product proofs and then run bullet proofs to do that. So on a technical level, what's the thing that you change in Armadillo?
Okay. So this is like very detailed difference. I think just to answer this question very shortly, we are slightly different in terms of how we form the like L2 norm proof. Yeah, but I think like both of these papers rely on a previous paper on verifiable PVSS by Shai Lubashevsky and another person. So like the core techniques there are like vastly the same, but I mean there's like little difference where we do like some optimizations on that. Yeah.
Excellent. All right. Thanks so much. So we're back at 2. There's lots of lunch options on Telegraph. If you're not from Northern California, I highly recommend getting a super burrito. This is our local specialty. But see you back here in a couple hours.